Hello everyone, I'm Priya, teaching assistant of course EE6102. Today we will discuss the core loss estimation using ANSYS software. So to do that, I have taken a simple example of an inductor whose dimensions you can see here. This inductor is having an air gap which can be variable if you want to change the permeability of the core. Then this is being excited by 4 number of turns, and the excitation is sinusoidal with a frequency of 10 kilohertz and the amplitudes of 10 sin omega 10. Sorry. Now the first thing we need to do is to draw this circuit in the ANSYS. Since Chauvin has already covered how to draw the circuit in ANSYS, I am not covering it here. And after drawing the circuit, we need to assign the material to the core to each of the windings. That is already being done here. After defining the material, the next thing is to excite the winding. So for that, I am making two windings, one winding with the positive current, another winding with the negative current. So let's define those windings first. So we are adding a winding here. Let's define this winding as winding P. Here you can give two type of excitation to the winding, either current or voltage. When you are specifying the voltage, it is asking for the other parameters such as input current, resistance, inductance, and voltage drop, which we don't know. So we are defining the excitation in the form of a current only. So let's define it. Then sine phi f, that is 10 kilohertz frequency, into time. Time is the inbuilt variable here. So the winding is created. Similarly, for defining uh, negative current to these four turns, I'm defining another winding here. Let's name it as winding N. Again, we are giving the same excitation to it because it's just the negative current in this winding of frequency 10 kilohertz and time. The current is in ampere. And keep that thing here in mind. We are keeping the foil to be a solid one, not the stranded one. So that is being defined. Now each conductor, we need to assign them as coil. Conductor 1 with positive polarity, and the number of conductors in this one is 1. So that is defined. Similarly, for other conductors also. Assign excitation to coil, conductor 2, number of conductors 1, positive current. Assign excitation as coil. Now, these conductors, we need to assign them negative current. So conductor, number of conductors 1, negative polarity, similar to the conductor 2 also. So we have defined each of these turns as a coil. Now we can assign this this coil to one of the winding. Let's say conductor 1 is assigned to the positive winding P. Similarly, conductor 2 is assigned to winding P. Similar for this also. Add to the winding P. And this conductor, return conductor, we are assigning to winding N. So here you see winding N is having conductor 1, 2, 3, 4 in the negative side one, and winding P carries positive current polarity. After this excitation, what to find out the core losses, we want the flux density inside the core. So how to calculate flux density from this current excitation? That is our next question. So to do that, one of the way is to draw the reluctance circuit for that core. So the reluctance circuit looks like this. It is being excited by the windings uh, Ni. Then Rc is the reluctance of the core and Rg is the reluctance of the air gap. Since the permeability of the core is very high compared to that of air, so we are neglecting the reluctance due to core, and the equivalent circuit will look like this. So the equivalent reluctance seen by the circuit will be Rg by 2. So now let's quickly see from the MATLAB program how to calculate the flux density. We will define the MMF by number of turns, that is 4, and current, which is 10 ampere in our case. Then we will find out the reluctance of the circuit, in which G is the air gap, which is defined here as 0.2 mm. Then mu naught is the permeability of air. AC is the cross-section area of the air gap. So that is being defined here, and which will give us the reluctance of the air gap. After that, from this reluctance of the air gap, we can find out the flux in the core with the formula of mmf by Rg by 2. Just now we have seen it come up from the equivalent reluctance circuit. From this flux, then we need to find out the flux density of the core. So we can divide this flux by the cross-section area of the middle limb. If we solve it, we get that the theoretical flux density expected is 0.2513 Tesla. So while doing the simulation, we should get the flux density close to this value. We will see while simulating it in ANSYS. So we have defined the excitation of to the windings. The next thing is to define the core material. Presently, I have defined one of the core material as ferrite, but if you want to change this material to some other one, let's say in our case we want to change it to 3C85. So to do that, you need to go to the properties of it. Yes, here there is an option to add material. So the BH curve of 3C85 is being shown here, which is for two different temperatures. One is for 25 degrees Celsius, this dark one, and 100 degrees Celsius. I have taken the 100 degrees Celsius data points, and that I will add up in my material. Here. So here, just go to the nonlinear permeability. You can define the BH curve. So I have already taken the data points. So I can directly import it over here. So this is my BH curve. Here the unit you can specify, this is millitesla. So I'm specifying here millitesla. So the permeability is being defined. Now to find the core losses, we need to define which type, how to solve it. So we are taking power ferrite formula, in which we need to define the CMXY. So using the power loss curves, power loss versus flux density curve for different frequency, we can estimate these parameters K alpha beta, which is actually CXY. So we are going to define these values here. So C is 12, X is 1.3, that is alpha, and Y is beta, that is 2.55. So we have defined the core loss parameters here. You can name this material as 3C85, let's say 2. Any name you can give it over here. Then click it OK and double click OK. And then you can assign the code with this material. After assigning the material and excitation, the next step is to set up a solution for it. So there are different solution type. You can see here magnetostatic, eddy current and transient. We want to simulate it for a fixed frequency of 10 kilohertz. So we can choose either eddy current or transient simulation. But eddy current simulation will give losses at a particular frequency only, and transient will give the losses at different frequency also. So I am taking here transient simulation just to show you, like if you want to give, if you want to find out the losses at different frequency also, how to do it. After defining the solution setup, the next step is to define the solution setup for this transient one. Since we are taking the uh, uh, frequency is 10 kilohertz, we will see for 3 cycles, that is for up to 300 microseconds, we will simulate it for up to 300 microseconds. And the time step in which we are want the solution is every 2 microseconds. So we have defined it over here. You can save the fields also. So every one step from 0 to 300 microseconds. 0 to 300 microseconds is being defined. Other things I am not changing, they are same. And then click OK. After clicking here, that solution setup will appear. Then to solve it, you need to press the button Analyze. It is taking some time, so I am not solving it here. I am directly showing you the results of it. So it's the same simulation. Only thing is I am going to show you the results. So to see the core losses, you need to go to Create Transient Report, then Rectangular Plot. Here you have the option to go to the loss and then to the core loss, and then click OK. OK means enter. After that, this core loss curve will appear. So first we need to see what is the current excitation we have given. So we have given a current amplitude of 10 ampere and for a frequency of 10 kilohertz, which means the time period will be 100 microseconds. So you can see here that for 100 microseconds, one cycle is completed with an amplitude of 10 ampere. Similarly, we have given it up to 300 microseconds. So you can see this cycle is appearing, 3 cycles are appearing. Then the induced voltage for the winding is coming like this. It is again up to 3 cycles, but you can see here that first cycle it is showing some random results, so we can't trust those results. From the second cycle onwards, it is giving us a proper core loss, expected core loss curves. So this part we need to, when we are calculating the core losses, this part we need to we should not take this part for the calculation. Now let me just quickly show you what is the flux density we got for this one. So the peak of that current will come up at 125 microseconds. So I'll show you the flux plot for that. So this is the flux plot for this geometry. You can see here that in the middle, this is close to 0.26, and our estimated value for the flux density from the reluctance circuit was 0.2513. So it's very close to what we have expected. This flux density is very close to it. Now, to find out the average core loss, we can export this data in the form of a CSV file and save it. Then in the MATLAB, you can find it out the average. Uh, yeah, you can find it. First, we'll plot it, the same data. So this is loss versus time. Uh, Now to find out the average loss, we need to take average from 100 microseconds to 300 microseconds. So that part is being done in this code. So uh, I'm taking here the mean from 50 to 150. This is 50 is basically the time where 100 microsecond is reaching. So I am taking the mean value from 100 microsecond to 300 microseconds. So let's see what is the mean, the average power loss here. So you can see the average power loss we got is 321 milliwatt. Now let's see theoretically what values we can get. So to calculate it theoretically, we have specified here the constants of 3C85 core, K alpha beta. Then we want to calculate it for the frequency of 10 kilohertz. The flux density theoretically we calculated as 251 millitesla. Then we are just applying the Steinmetz equation here. And Steinmetz equation gave us the average loss per unit volume. Then we need to multiply the core loss with the core volume to get the average core loss of a core. So the average core loss theoretically which we are getting is 278 milliwatt, and experimentally we are getting 321 milliwatt. So the percentage deviation in the core loss is 13%. 13% is a huge deviation. Now, uh, now the question is why this deviation is coming up. This is because if you see here our flux density plot, the flux density is changing. It is not same in the entire cross section. To validate it, like our Steinmetz equation is valid only for a uniform flux density. So to get that, what we are doing is, so you can draw the polyline over the circuit to find the uniform, to find the flux density over a distance. So to do that, I am taking this simulation and just go to draw, then line, draw the line from here to here, let's say, just stop it. So this is the polyline which is being created over here. And similarly, if you want to find out the flux density from in this region, then again you can draw another polyline from this point to, let's say, this point. Now to how to find out the flux density over this line. So to do that, just go to results, right click on that, go to field, create field report, rectangular plot. Here is the option to select the polyline. While selecting the polyline, you can select the magnetic, flux density magnitude vector, and then just click enter. So if you click the enter, you will get uh, the plot of flux density over the distance where we have drawn the polyline. You can find this plot for 1 minute. Yeah, for different time durations also. For example, if you want to find it out for the uh, peak flux density point, then you need to specify the time or duration here for it. Similarly, the magnetic flux density plot over a distance, here you can find out. Then now to find out the mean value of the flux density in that region, you can again export it as a CSV file, then find the mean in the MATLAB, and then that mean value you can use in your this Steinmetz equation, and then trying to correlate the power loss of this flux using Steinmetz equation, and that we got it from the FEM. And you can see a good correlation between them. You can calculate it by yourself. Another point I want you to notice here is that if I'll plot the flux density plot here for peak value, then you can see that the flux density is not uniform in the entire cross-section area. Okay, it is having a very low flux density in this corners and in the outer corners, and higher flux density at this inner corners. So to avoid this thing, what we can do, we can draw another geometry where we can find out a almost uniform flux density. So to show that, I have drawn here a U kind of UU shape course I have taken, and its symmetry is being drawn. Here you can see that the area is almost uniform in this region. So let's see what kind of a flux density plot we can get from it. So yeah, so here if you see, the flux density is quite uniform compared to that of a previous case. So if you apply the Steinmetz equation for this kind of a geometry, it will give you a more closure result to that of a FEM. Yes. That's all in the core loss video. Thank you.